Hello, everybody. Welcome back for Friday's class, our last class before the exam, which is in an hour. Hello, Danielle. Nice to see that you're here. Who else is here? Say hello in the chat. Emma, happy exam day to you as well. A lot of energy in the chat today, it seems like. Good morning, Sam. Hello, Liza. Glad to see that you're both here. Avik, hello. Miriam, good morning. All right, in about a minute or so, we can get started. How's everybody's week going? Almost over. And then we got a short week next week, right? We only have we have no class on Friday next week. Good morning, everybody. It's 9 o'clock, so we can do the simultaneous sip and then get started with the final material before the test. All right. All right, let me know in the chat if you participated or not. I think the participation levels have been lacking lately, but it's good luck to have a simultaneous sip before your exam. Good morning, William. Okay, so here's the plan for today. Okay, there's a few. The plan for today is we're going to finish up 5.5, which should take, I'm hoping, not too long. We have a couple definitions of theorem and then one example. Emma and Emma's sister both did the sip again. That's nice. And then once we finish 5.5, I'm gonna open it up to questions from the review packet or any other questions you may have. So so be ready to ask me some questions about any of the material that you want to ask me about. Okay. Okay, so just a little bit more notation or definitions, I guess, about complex numbers. Okay, so we had vectors. We were looking at vectors that had some complex components. And so the real component, so the real and imaginary parts of X are the vectors which we'll denote by RE X and IMX, and Rn formed from the real and imaginary entries of X. Okay, so just this notation. REX means the real components, IMX is the imaginary parts, and we're going to factor out the I. So we're going to treat them both as vectors in Rn. So for example, if X is the vector 3 minus I, 2 plus 5I, find the real and imaginary parts of X. Okay, there's going to be 3 parts to this question. Find X conjugate. Find X conjugate, the real components of X, and the imaginary components of X. If you feel like you have the answer, feel free to share in the comments. But this is really straightforward here. So X bar, or the conjugate of X, or the complex conjugate of X, I guess. We keep the sign of the real components the same, but we change the sign for the negative components. So it'd be 3 plus I, negative I, and 2 minus 5I. Right, so we find the complex conjugate of each of the components. The real part of X is just we read off the coefficients of the terms that aren't multiplied by I. And the imaginary parts, we read off the coefficients of I. Okay, so we don't include the I's here, right? Because part of our definition says they live in Rn, they don't live in Cn. Okay, and you could check, it's a fact that X is equal to real X plus I times the imaginary components of X. Okay, so this gives us a way to take a complex number and basically break it up into 2 real vectors. Take a complex vector and break it up into 2 real vectors. And we'll just have to remember that there's a factor of I here. So if you have any questions on this example, feel free to type it in the chat, but I'm going to state the next few theorems, and then we can get on to the last example. So this theorem we observed yesterday. The theorem says if lambda is an eigenvalue, of some matrix A, and X is its corresponding eigenvector, the theorem says then the complex conjugate of lambda is also an eigenvalue. Okay, so if we have A plus BI is an eigenvalue, then A minus BI is also an eigenvalue. and its corresponding eigenvector is the complex conjugate of x. Okay, so if we looked back at that example from yesterday, we had that 2 plus I was an eigenvalue and 2 minus I was an eigenvalue. And if you look at their eigenvectors, they're complex conjugates of each other. Okay, so this says if we can find one complex eigenvalue, we automatically get a second one for free. And similarly, if we find its eigenvector, we find the complex conjugate's eigenvector for free. So this is just a good way to save a little bit of time. And now here's a theorem, another theorem. So let A, this theorem basically, let A, lowercase, capital A here. This next theorem kind of uses this first theorem as the proof of this theorem will rely on this, but we're not going to do the proof. So let A be a real two by two matrix. Okay, so real meaning all the entries of A are real numbers. And suppose that A has a complex eigenvalue lambda equals A minus BI. And the eigenvector associated to lambda we'll call V. Okay, so this is our setup. We have a 2 by 2 matrix we have a complex eigenvector and its associated eigenvector we call V. The theorem says then we can express A is equal to P times C times P inverse, where P is the matrix whose first column is the real component of V, whose second column is the imaginary component of V. And C is the matrix A, B, minus B, A. Okay, so this isn't quite diagonalizing A, but we can't diagonalize A. The best we could do is have not a diagonal matrix, but kind of this anti-symmetric matrix. All right, and it's going to be, there's going to be some applications that we'll see where it's useful to express a matrix as something times this anti-symmetric matrix times P inverse. Okay, so let's take a look at an example, and this will be our last example before we move on to just studying for the test. Or reviewing for the test, I guess. Let's see if we can use this theorem and apply it to an example. Okay, so the example says find an invertible matrix P and a matrix C of the form A, B minus B, A. So basically, let's find P and C such that A equals P, C, P inverse, where A equals 1, 1, negative 2, 3. Okay, so this was the same matrix we looked at yesterday, but just for the sake of practice, we could go through and find the eigenvalues and eigenvectors again, just so you have it in your notes. But does somebody want to explain how we're going to solve this question? Or if they're not sure, just maybe tell me that you're unsure. Not sure. Okay. Yeah, so this theorem tells us how we're going to do it. We have to find an eigenvalue and find its eigenvector. And then the theorem tells us the rest of the work. So how do we find an eigenvalue? We need to find the determinant of A minus lambda I and set it equal to 0. And the solutions of this equation, which we call the characteristic equation, gives us the eigenvalues. And then we want to find a basis for the null space of A minus lambda I when we plug in lambda equals A and B would be certain numbers here, depending on the example. Okay, so I'm going to start working this out, but if you could obviously mute me at any point and try to work it out on your own and then unmute me. So A minus lambda I is the matrix 1 minus lambda, negative 2, 1, 3 minus lambda. So its determinant is 1 minus lambda times 3 minus lambda minus negative 2, so plus 2. Which is lambda squared minus 4 lambda plus 5. We want to set it equal to 0. The way we solve this quadratic is with the quadratic formula. Lambda equals 4 plus or minus the square root of 16 minus 20 over 2. Which you can do the math. It simplifies to 2 plus or minus I. The theorem says we want it in the form of 2. We want to use the minus version to use this theorem. It doesn't really matter, but so we'll use lambda equals 2 minus I. So here, A equals 2, B equals 1. All right, is that clear how I got A equals 2 and B equals 1? Yeah, if we're using the notation from over here. And now we want to find the corresponding eigenvector to this eigenvalue. So we look at the matrix A minus 2 minus I. And we get this matrix. How do we row reduce this matrix if we have a complex entry in the first location? So what do we multiply the first row by when we're dealing with this, when we're dealing with complex numbers? If you're unsure, look back in your notes from yesterday. Yeah, the complex conjugate. So yeah, -1 minus I will multiply to the first row. Oh, sorry. There's a little bit of a typo here. -2, -2. This should be a -2. So when we do the complex conjugate, -1 plus I times -1 minus I becomes 2. Again, you could try that on your own. The next entry is 2 plus 2i, 1 plus I. Right, and this row reduces to 1 plus I, and then 0, 0. And I guess like technically we're trying to set this equal to 0, so let's make this an augmented matrix and have a row of zeros at the end, a column of zeros at the end. And so we have x1 plus 1 plus I, x2 is equal to 0. Which works out to this. And now our theorem says in order to get C, we've already done all the work. We know what A and B are. In order to get P, we need the real part of our solution and the imaginary part of our eigenvector. So the real component is -1, 1. And the imaginary component is -1, 0. Okay, and so P is the matrix whose first column is the real component, whose second column is the imaginary component. And C is the matrix AB, -B, A. So 2, 1, -1, 2. Okay, and you could check the theorem tells us that A is equal to -1, 1, -1, 0, 2, 1, -1, 2, times the inverse of this matrix. Okay, so ask any questions you have about complex eigenvalues or eigenvectors first, and then we can move on to questions about anything else you want to talk about. But this is the last example. The Washington Nationals are going to be World Series champs 2 years in a row thanks to coronavirus. Go Nats. You saw my shirt. It's the Red Sox 2004 World Series champ Hawaiian shirt. Okay, sorry. On the test, should we solve for the inverse or leave it like that? And do we have to multiply it out? No, leaving it like this is perfectly fine. Right, if you were to multiply it out, you just get back to what we started with. You would just get 1, 1, negative 2, 3. So that's how you could check your answer. If you want to, if you're not sure if you're right or not, you could find this inverse and then just do out the big multiplication to make sure you actually have the matrix we started with. But no, on a test, leaving it out like this is preferred. Yeah, and the reason why we do this, and I'm hoping we'll get to some applications in a few weeks, is it's really easy to compute a raised to a high power. And we saw yesterday that, or maybe it was 2 days ago, that like the matrices that have complex eigenvalues tend to be like rotation matrices. And a computer, like when you're programming, a computer uses rotation matrices all the time. Think of like when you're rotating something on Snapchat or whatever app you prefer to use. What's happening behind the scenes is you're multiplying by a rotation matrix. Can we use lambda plus 2i? Yeah, if we used lambda plus 2i, we'd have to switch our value of b. So b would become -1. So b would become -1, and we'd have to find a different eigenvector. But the result would also hold. So our b values would be different, and then the eigenvector would be, our b values would be different, and then the eigenvector would be a little bit different, but it would still work. Can we have office hours this weekend? Kind of a stretch, but I thought I might ask. If you have a question, just send me an email, and if it's easier to Zoom, we could Zoom. But I'm not going to have any planned office hours. Yeah, so it could be good practice to see what happens if you used 2 plus I to work out the solution. Like, so what's going to change is the imaginary component, this would switch signs, and then these would switch signs. And this would switch signs. So yeah, so there'd be a couple of columns that are switching signs. So are there any questions from that review packet that anybody wants to go over? Or anything else in general? Can you go over the kernel, what a kernel is again, and go over 3 and 4 on page 5? Yeah, okay, so I'm going to erase all this. Let me get up the questions. Okay, yeah, so 3 and 4 both have to do with the kernel. So we'll start with 3, because that will be like, that tells us what the definition is. And then 4, we could prove it's a subspace, or at least talk about how to prove it's a subspace. Okay, so this is page 5, number 3. All right, and we have L. I know we typically use T, but L for linear transformation, I guess, today, is a linear transformation from V to W. And the question is, define the kernel. Which we denote by kernel of L. So this is more of, do we know the definition of what the kernel is? So does anybody remember what the kernel of a linear transformation is? And then question 4 will be actually using this definition. Right, so what this looks like without the kernel. Over here is our vector space V. Over here is our vector space W. And there's some map that sends the vectors in V over to the vectors in W. So what is the kernel of this map? It's okay if you don't know, because it's an open book, open notes test. So you don't have to really memorize anything. But yeah, so what is the kernel? It's, well, somewhere in W, there's this vector which we call 0. Yeah, it is a subspace of V. We're gonna prove that for question 4. But it is a subspace of V that has certain properties. It's all of the vectors in V that get mapped to 0. Okay, so the way we write that is the kernel of L is equal to so all vectors, which we call V in our, yeah, exactly. All vectors in V that get sent to 0. So all vectors V in V such that if we evaluate the linear transformation at that vector, they get sent to 0, or the 0 vector in W. Okay, so for example, let's say L is the derivative map from calculus. Okay, and V is equal to Pn, and W is also equal to Pn. Right, because the derivative of a polynomial is also a polynomial. Okay, so that's this is a linear transformation that satisfies the properties above. The kernel equals the polynomials in Pn that get sent to 0. So whose derivative is 0? Which polynomials satisfy that property? You take their derivative, it gets sent to 0. It's the constants. So in this case, the constant polynomials would be the kernel of this map. That's just an example. All right, so the kernel, just again to recap, is the set of vectors in our domain that get sent to 0 under the map, whatever map we were given. So in my example, I said it was the map that sends a polynomial to its derivative. And yeah, so the only polynomials that get sent to the 0 polynomial are constants. Okay, so the next question was prove that the kernel of L is a subspace. And we'll do it using the 3 properties. So what are the 3 properties of what 3 properties need to be satisfied in order to show something as a subspace? Yeah, it has to contain a 0 vector. And then I'll finish the other 2. It has to be closed under addition. And then closed under scalar multiplication. Okay, and if we can confirm all 3 of these properties, then we show it's a subspace. Okay, so show that the kernel is a subspace. So okay, so the first thing we want to show is 0 is the 0 vector in the kernel of L. And another way to write that is L of 0 equal to 0? And hopefully the answer is yes, but can somebody justify why this is true? And while you're thinking about that, I'll write out the next part. Okay, so maybe we're not sure why this is true. So is 0 in the kernel of L? Well, that's another way to write that. Instead of using this kernel of L notation, that's just asking if we evaluate 0, under this linear transformation, do we get 0? The answer is yes, because that's one of the properties of a linear transformation. So you have to go back and look at our properties of linear transformations. They always send the 0 vector to 0. So yes. Okay, so that's the first thing. We showed condition 1. Now we want to show that it's closed under addition. So that's to say, if we have two vectors in the kernel and we add them together, is it still in the kernel? Okay, another way to say that is if we look at the image of u plus v, do we get 0? Okay, and so let's just start with what does it mean for u and v to be in the kernel? It means L of u equals 0 and L of v equals 0. Okay, so that's what it means for u and v to be in the kernel. And so let's take a look at L of u plus v. Well, I claim we can break it apart. So why are we allowed? Why are we allowed to separate with addition? So why is this step true? Well, I'm sure you're all screaming at the top of your lungs at your keyboard saying this is true because this again is a property of linear transformations. Okay, and now, well, we know L of u equals 0 and L of v equals 0, so we're done, right? So L of u plus v is equal to 0 plus 0, which is equal to 0. Hence, u plus v is in the kernel of L. Okay, so we showed that it's closed under addition. I'm getting no feedback right now from the chat. So somebody give me a little bit of a response saying that I'm crazy or that this is easy or that this is really hard. So the last part is we want to show that it's closed under scalar multiplication. As to say, if u is in kernel of L, is cu in the kernel of L, i.e., is L of c times u equal to 0 for all c? I understand now. Good. Yeah, see, a lot of this stuff, probably in class, it went quick because we go pretty quick. Yes, Noah, thank you. It is, we'll use a linear property of linear transformations as well to finish this off. Okay, so let's just take a look. Okay, u is in kernel of L, so we know that u, I'm sorry, what does it mean to be in the kernel? It means L of u is equal to 0. So let's look at L of cu. We're allowed to factor out the c because this is a property So L is linear. And so this is equal to C. L of U is equal to 0, so C times 0, which is equal to 0. Right? So thus CU is in kernel of L, and we hit all three of the check marks. We showed that it is a subspace. Any thoughts or questions or reactions to this proof? Right, so if you had a question that was like, show that something is a subspace, you know, you can just check off, make sure you can check off the 3 boxes. You're welcome. Yeah, we have other ways to show something's a subspace. Right now that we know that the kernel is a subspace, we could, if we show that something is you know, the kernel of some map, then that automatically tells us it's a subspace. Similarly, with if we show it's the span of some vectors, remember we had that was another easy way to check if something's a subspace. But yeah, in general, what you should do is figure out what is the 0 vector in this vector space, right? The 0 vector when we have column vectors is the thing with all zeros. But if we were dealing with like polynomials, for instance, the 0 vector would be the polynomial p of t equals 0. If we're dealing with functions in general, continuous functions, again, the 0 function would be the function f of x equals 0. Okay? And then you'd show, is that in our, does that get mapped to 0? And if we add 2 polynomials together and then evaluate the map, is that still 0? You know, we have to show all 3 of these properties. I think we have time for one last question if anybody has one. But if not, and feel free to just ask, but I'll talk a little. So you could use your notes, you could use your book, and you could use what I've posted to Canvas or to YouTube. Those are, but don't use anything else, okay? If you have answers that are suspicious from Chegg or any other website that you could find on Google, like I'm going to be able to tell, and don't do this for a test. So use your own work for the test. You could use the book, you could use your notes, you could use my YouTube videos, and you could use anything I posted to Canvas, but do not just search answers online, because I'll be able to tell and I'm not going to be happy about it. But I would recommend start today, you know, crank out the easy ones today. You know, and then get a sense of what the challenging questions are going to be, and then yeah, attack those tomorrow. For proofs on the test, do we need to cite where our definitions come from? Like say from the notes, or say it's a definition? If you're talking about like being like linear, for instance, I mean, it doesn't hurt to cite it, but if you just say it's from the notes, that's also fine. All right, well, if there's no other questions, you guys will do fine. It'll be up on Canvas in 2 minutes. So take a look. And And yeah, make sure it's your own work. No working with friends on this one, okay? But yeah. All right, you know the drill. Make sure you hit the like button before you get out of here for good luck on the test. And email me if you have any questions. I'll be checking my email pretty often because there's nothing else to do. All right. Bye-bye. Good luck.